Good morning. Welcome to the last distinguished lecture for this semester. I'm Anurag Gasman. I'm the Associate Director of ISTEC. For those of you who are not familiar with ISTEC, maybe there are few. ISTEC is a university-wide organization for promotion of research and teaching in information sciences and technology. So it's my great pleasure to introduce today's speaker, Ashok N. Srivastava. He recently became the Senior Vice President and Chief Data Officer at Intuit, and will be creating a global team focused on large-scale machine learning and artificial intelligence. About 4 weeks ago, he was the Vice President with Verizon, where his global team focused on building new revenue-generating products and services powered by big data and AI. He's a consulting professor at Stanford in the electrical engineering department. In spite of his work in industry, he is actually an active researcher and does a lot of work. So he's the editor-in-chief of AIA Journal of Aerospace Information Systems. He's a fellow of the IEEE, AAAS, and AIAA, which is the American Association for the Advancement of Institute of Aeronautics and Astronautics. He was the principal scientist for data science at NASA Ames Research Center. And he has had major engagements as a private consultant to companies such as IBM. Dr. Srivastava is the author of more than 100 research articles in data mining, machine learning, and text mining. He has edited 4 books on related subjects. He has 5 patents and more than 30 under file. He has won numerous awards, including the IEEE Computer Society Technical Achievement Award for pioneering contributions to intelligent information systems. He won the NASA Exceptional Achievement Medal. He won the Distinguished Engineering Alumni Award from the University of Colorado Boulder and IBM Golden Circle Award. Ashok does have some connections to CSU. Some of us old-timers know Professor Jagdish Srivastava, who is Ashok's father. He has had a long and distinguished service as a professor in our own statistics department. One of the notable things, in addition to his distinguished service, is in the aftermath of the floods that we had at CSU back in 1997. Senior Dr. Srivastava donated several tens of thousands of dollars worth of books and journals to CSU library. Ironically, we became reconnected when Ashok contacted us to donate some additional books to the library. So it gives me great pleasure to introduce Dr. Srivastava.
Thank you so much for that very kind introduction. It's really amazing for me to be here at CSU. So I was literally born and raised in Fort Collins. I was born at Poudre Valley Hospital. I grew up about 5 miles from here, north of here. And I grew up in the courtyard that's just outside of this building. So for me to come back and to be able to address all of you and talk to you about some of the work that I've done over the years is particularly exciting and very rewarding. And so I really want to thank Bruce and the entire organization for inviting me to come here. I've been looking forward to it since the very first time he asked me to come about a year ago. So my name is Ashok Srivastava. I am the Senior Vice President and Chief Data Officer at Intuit. And this just happened. I think I've been there now 4 weeks, so I can tell you all about it if you've got any questions about what's going on there or anything. I know really pretty much everything that's happening. I'm just joking. So before that, I was at Verizon and many other places. And what I thought I would do today is talk to you about the work that's going on in large-scale machine learning and artificial intelligence, but from a cross-industry perspective. So we all hear about these amazing opportunities in AI and these amazing innovations that are happening in AI and machine learning, and they're incredibly exciting. But they have a foundation in certain areas that I'd like to explore with you a little bit and talk to you a little bit about the cross-industry perspective that at least I've been able to enjoy over the last many years. So I couldn't start this talk off without giving you at least one retro picture. So can anybody guess where this is? Take a guess. Somebody? CSU. Yeah, that's CSU, good. And this is not far from here. As I was driving up here, I noticed the same building. This is my father, my mother, and my brother and sister. You'll notice that there's not me on the picture there, and that's because I wasn't born yet. My dad came here in 1966 as a professor in statistics, and I think this is one of the early pictures that they took. I was looking for different pictures of CSU as I was going through our archives, and this is one that seemed to include my family and everything. So with great respect, I'd like to dedicate this talk to my family. So if you look at data and the way we've used data as a society over history, it's really interesting to think about it. So if you go way back, a long time ago, and start looking at the way people studied data, it was a situation where they had few observations with relatively low noise, and they tried to use that information to get some insight into the way the world operated. And so you could look back a long time ago, think about what people were doing with harmonic oscillators, understanding these things. And as they did it, and as they started to explore it, they also started to realize that physical models could really give insight into the world around us. And so the great scientists of past, like Newton, Leibniz, and many others, started to form a worldview that was based in physics, right? And that physics, one of the governing laws, one of the governing operators in physics, were differential equations, still is differential equations, integral equations, and they used that to build an understanding of the world around us. So that was a world in which there was relatively small data volumes and tremendous amount of information in those data sets, and also tremendous insight that was being garnered about the world around us through the use of physics and through the use of those types of equations. Now, this green curve shows kind of, therefore, high information value per record or per observation that you got. So if you think back to what Kepler did, that analysis that Kepler did, there were relatively few observations, but tremendous insight was garnered from it. He discovered, along with others, how the planets circulate around the sun. Now, as you move forward in time, so pick some time like 2015, something like that, you start to see these enormous data sets that are being generated. So if you look here, it's almost off the scale in terms of data set sizes with these large-scale internet applications, astrophysical applications, and other applications. But the information value per record is relatively small. So if I told you that I looked at CNN.com yesterday, it doesn't tell you a lot about really anything. And if I told you that a certain snippet, an ad was served from Yahoo to me yesterday at midnight, it doesn't tell you really anything. And if you have a lot of information like that, it's still per observation relatively small amount of value. Now, what's interesting about that, so we're now in the situation where we've got a huge amount of data, not much information value per observation. And so you say, well, does the world of physics, or does the world of these very powerful equations, whether they're coming from observation or not, how is it going to help us? And the fact is that you can build some models, but those models tend to be relatively primitive. And the reason for that is it's hard to express and capture the complexity of the world around us that's coming, let's say, off the internet or off of other kinds of non-physical observations. It's hard to capture that and quantify it and build PDEs to describe how it's going to work. Some people have tried to do that, but generally speaking, we find it's difficult. And that's where data science comes in. So it's this amazing thing. So it used to be called statistics and computer science and all of these things. And if you start to look at the intersection of large-scale computing with statistics, you start to see the emergence of data science and machine learning as prominent fields to help understand what's going on in these massive data sets, when you don't have physical laws that are governing the generation of those data sets, right? So I always think about this, and I always look back into history, because as you look into history, you see societal changes that are occurring, in the sciences at least, where we're moving from a world which this was dominant to another world where data was dominant. I want to point out, though, that this does not imply, in my opinion, that physical models are less important. I think they're incredibly important, but they can be informed through the use of data. So I've been very fortunate to have quite a large number of different kinds of viewpoints on this theme of data and understanding things around us. So I went to school at CU. I got my PhD there, and I worked at NIST for many years. I'll talk to you a little bit about that. IBM, a small startup called Blue Martini Software, NASA, and then a period doing venture capital at Trident Capital. And then I was at Verizon most recently. I have affiliations with Stanford and Intuit and these organizations down below. And as you look at it, you know, it's kind of odd, I suppose, to look at something like NIST, where I was doing applied superconductivity, IBM, which was kind of industrial consulting in a large number of areas, Blue Martini, which was really focused on consumers, NASA, which had nothing to do with any of that. It was all focused on aerospace and earth sciences and astrophysics and so forth. But the thread that connects all of this is data. And it's the understanding of data, regardless of where I worked, whether it was at NIST trying to understand how superconductors work, at NASA trying to understand, let's say, something in astrophysics or earth science or aeronautics, or now at Intuit trying to understand consumer finance. It's all the same. And what's really interesting about it is that physics plays a role in some of these places, but not all of them. So certainly at NIST and at NASA, physics played an important role. Having those deep understandings of the dynamics of the data generating process was very important. But at other places, it was virtually impossible to think of those kinds of models, like at Verizon and so forth. So I'm going to take you through a little picture of that. But first I'm going to start with NIST. So here I worked as a student in high and low temperatures superconductivity, doing things that we would call today anomaly detection and prediction problems. It was extremely interesting because we had data coming in at an incredible rate for the time. I was reading one of the original papers that I worked on when I was there. We had about 9 million observations from one sample that we were running. And today that's not really very much, but back then it was a lot. And I'll show you why I say that. We did statistical data analysis and real-time control systems, which was a fabulous way of understanding physical systems and then data systems and how these two things come together. So I have to show you, this is a picture. I wish I took it, but I didn't. I got it off of Wikipedia. But it was what really excited me, this idea that you could have a superconductor at relatively high temperature, this is liquid nitrogen temperatures, hovering over a cylinder here, and that hovering is due to what's called the Meissner effect. And so as this dwells over there, it's literally hovering. And my boss used to say that this is pretty much an electric levitating train with just a few details that need to be worked out. So I always thought of working out those details. But let me tell you why this was of great interest to me. So we had a lot of data coming off of these superconducting systems, whether or not they were high or low temperature systems. And they were going into machines that were kind of like this. This is the HP85 and then its successor, which model number I've forgotten, but not much more than that. And the question was, as this data came in off of those systems, could we in real time understand if the observations that we're getting at this moment are correct or not? When you work at a place like NIST, the correctness of the observations is very important. And I'm very indebted to my first boss for giving me that kind of understanding and the opportunity to understand and work in this kind of a situation. So we worked in a number of areas, and one of them was developing software techniques to improve data reliability in superconductor and low resistance measurements. And the reason I highlight this is because it was a place where I started to see the idea of anomaly detection and measurements from nanovoltmeters. So these were making measurements at billionths of a volt. We took about 10 million measurements. And we also started to develop these real-time systems. And here's a graph from that paper showing errors that actually occur. These drops are actually errors that occur in nanovoltmeters that we were working with. And I started to see that a couple of things, which are, I'm sure, completely obvious to you. Number one, that the data that you get is not necessarily representative of reality, right? That there can be errors in it, even if it comes from the machine. This is an example. That if you're going to do real-time system and real-time processing of that data, you need to be able to intervene as the data comes in and make some intelligent decisions. So this was, in my mind, kind of the genesis of the way to think about data and the way to think about these kinds of problems. So I'm going to skip it forward now over IBM and some of the other places and talk a little bit about some work at NASA. So here, the idea was to do large-scale machine learning applied to a very large number of different enterprises at NASA, including aeronautics, space systems, earth science, astrophysics, and everything. Extremely interesting. And the reason it was interesting, because I love these application areas, but physics plays a different role in each of these areas. First of all, one thing to note, it does apply in almost all, if not all, of these areas, as opposed to a consumer situation where it's very hard to build physical models. We had massive data sets, and we started to explore distributed computing. And the same ideas of anomaly detection now added with diagnostics, prognostics, or prediction and mitigation started to play a role. This is the beginning of use of machine learning in those areas from my perspective. I don't mean for, across the field, but for me, this was a place to start using these techniques at scale on a large number of different application areas. So let me tell you a little bit about some of the work that we did. So we faced, at least at the time, a big data challenge. So one of the areas that we worked in was aeronautics. So if you think about the aircraft that you and I fly on probably a very regular basis, those aircraft have a large number of sensors associated with them, and they're telemetering data back to a central hub. And when the airplane lands, that data is transmitted to another hub that my team and my previous colleagues built that goes into repositories that can analyze data. And right now, at least at the time, there are about 10 million flights per year in the United States alone. And most of these flights, you record about a few hundred, so let's say between 300 and 1,000 parameters per flight are being recorded, and they're at about 1 hertz, which means 1 measurement per second is being taken. And we also have radar track data from around the country that are watching these airplanes fly. And we also have text data. And that text data comes from reports that the pilots write about their flights. So they might say, you know, I was flying along to LAX and I saw this incident, or there was this problem on the aircraft. So there are a lot of text reports that come also. So this is a heterogeneous type of data set where you've got structured data, some semi-structured data. At the time, there were about 100,000 reports that were coming in. I think there are much more than that now. And these reports were placed into different categories by humans. We started to build text mining systems to put them into categories automatically. And the text reports, interestingly enough, because of privacy reasons, are not linked with the flight data. So you could have a flight, for instance, that goes from, let's say, Los Angeles to New York, and you'd have all of the telemeter data from that, but pilot might have written a report, but you're not allowed to link them. And you're not allowed to link them. I see some reaction to that. You're not allowed to link them for privacy reasons, safety reasons, and so forth. But it poses an interesting challenge because there might be a report out there that's of use to understand what's going on the flight itself. So this was the nature of the data that we had. Let me show you what one of these real reports looks like. So just prior to touchdown, this pilot writes, LAX tower told us to go around because of an aircraft in front of us. Both the co-pilot and I, however, understood the tower to say, cleared to land. So I'm not going to read the rest, but just imagine you're landing at LAX, and you're like, wait, there's a plane down there. That's not right. And so the pilot takes some action. This happens a lot. It actually happens quite often in our air system. And yet the accident rate is extremely low. And the reason for that is it's quite a robust system. My team and I were working on ways to use data mining and machine learning in order to understand these kinds of reports in conjunction with the data that's coming in off of the aircraft in order to make better decisions about safety. And so this gives you an idea of the type of data that we had. Now, if you think about it, I don't know how many of you are familiar with different anomaly detection approaches, but generally speaking, anomaly detection is not that hard. If you've got a string of numbers and it kind of fluctuates like this, and then you've got a spike like that, and then it comes back down, it doesn't take too much to say maybe that spike is anomalous. You can create some statistical tests to check for that. And if in fact it is anomalous, then you say it's an anomaly, and then you can go and do something else. So that's basically how it works. If you have high dimensional data, let's say you've got a few thousand dimensions, or you've got a few million dimensions, that's even higher dimensional data, then it becomes a little bit more challenging, and we created methods to deal with those situations. Now, that approach works if you've got numeric data, but here I've got an example of text data. The question is, how do you fuse these together? So we developed an algorithm, which we called MCAD, Multiple Kernel Anomaly Detection Algorithm. And those of you who are familiar with machine learning will know that kernel methods are kind of one way of doing and building models that can do predictions, anomaly detection, and so forth. And those kernels are essentially mathematical ways of measuring if two things are similar. So if you've got a kernel function, and the kernel function takes two inputs, x and y, it tells you how similar x and y are. If x equals y, it gives you a certain number, and if x does not equal y, then it gives you a different number. And there's a way of constructing these kernel functions. They have to be positive, definite, and so forth. But what's really interesting is we started to think about ways of taking different kinds of data, like discrete data, text data, network data, and continuous data, and fusing them into a single kernel, and using that kernel in order to do anomaly detection and prediction. I wasn't aware at the time, at least, of this type of an operator being created. And the fact is that it worked extremely well for this application because of the nature of data that we had. So we had discrete data, which are the pilot inputs that he or she is making into the cockpit as the individual is flying the airplane. So when the pilot says we're going to go down from 40,000 feet to 30,000 feet, he or she would flip a few switches, maybe change something on the flight computer, and then the airplane obviously would obey and then go down to the new altitude level. So that's input from the pilot into the airplane. Then another source of data are radar data that's coming from the network surrounding the aircraft. And so this is an example or a picture of a simulation of flights in the US at one snapshot in time. So there's a lot of traffic, a lot of data comes from there. I already told you about the text data that comes through. Each of these data sets gives a different view on what's happening on that aircraft. So the question is, how do you fuse all of this together? So if you'll take a look at this next slide, it gives you an idea of the way we think about it. And the idea here is for you not to say, this is the way to solve the problem, but it gives you an idea of the way we try to bring data sets and machine learning together in order to solve these kinds of problems. So for those of you who are familiar with kernel methods, this might seem clear to you. For those of you who are not, let me describe it a little bit. It's not really that complicated. I already said that in this example, there are two data sets. There's discrete data and continuous data. So KD is a function that takes two data sets or two data inputs, xi and xj, and KD just measures whether or not they're the same or not. If they're the same, it could emit the value of 1. And if they're different, it might emit a value of 0. And if they're kind of in between, it'll give you some number in between, like 0.6 or something like that. That's what K does. So it's a function that takes values, and it measures the similarity for discrete data sets. And KC does the same thing for continuous data sets. And if I copied another equation, it would have another one, KT, that measures the similarity between text data sets. So you can see here that I've got a weighted sum, KD and KC. They're weighted by these numbers beta, which we can control. So that's a parameter that we can control. If we set beta equal to 1/2, what happens is that it says Q is somehow equal to half discrete data, half continuous data. If I set beta equal to 1, it would say it's all discrete and no continuous, because this number becomes 0, right? So it's a way of constructing a cost function. And the cool thing is, once you've got a cost function in machine learning or in statistical applications, you can do all kinds of neat things, such as do optimization on it. So we say we want to minimize this value q subject to certain constraints. When you do this minimization, these alphas turn into ways of understanding the data set and making predictions. So we wrote a bunch of papers on it. There's one. But many, many people have worked on this. I don't want anyone to think that we invented this type of an approach. What we did do, though, is we created these new types of kernels, which are additive kernels that can fuse data together. And let me show you how this works in real life. So let's think back to that situation where an airplane is coming in. This is an LAX runway here. And an airplane is coming in. And take a look what happens. It comes in like this. It actually does a sweep around a loop, and then it comes back down, and it lands. And that sounds like good news, except take a look. There's this Flight 11 that's coming in blue, and it came within 1 nautical mile of a collision. This is a quite interesting example because it's not like there are only 2 airplanes in the sky. There are a lot of traffic around LAX at any given time. And to detect something like this is actually quite difficult because how would you do it? So you could sit in front of the radar screen and watch, which is what actually a lot of people do. You could build an algorithm that says, let me look for loops. And so you'd look for a loop in your stream, and if you find a loop, you might say, maybe that's indicative of something. But here the idea was to say, we don't want to make any prescription about the kind of anomalies that we're going to see. We want to build that kernel algorithm the way I described. We want to optimize it and then discover what types of events are occurring. And that's how we discovered this. And there are many other events that were discovered through this approach. So it gives you an idea of taking data, a lot of data, taking an algorithm that we constructed, applying it at scale across a very large amount of traffic, and then discovering, and this is just one example, but there are many other examples of anomalies that might have safety concerns or safety issues associated with them. The whole idea is that if you're able to discover that, then you might be able to take corrective action in order to minimize the number of events like this that occur. So we were able to do this in many cases, and I'm very pleased to say that in conjunction with Southwest Airlines, we deployed similar algorithms there that are operational, that are actually, they told us, discovering operationally significant events, which is a way of saying that they are discovering things about the way people are flying those airplanes that have safety implications. So if we look at the way this was all done, it's a combination of a couple of things. First, a lot of data, algorithms, and then people also. So the domain expertise necessary to understand these kinds of situations and discover them needs to be always taken into account. And we actually built and modified our algorithms based on the information that we got from pilots and from other experts in this field. So I'm going to switch to another aerospace application because it's really quite interesting. So hopefully you all remember the shuttle. It was one of the most interesting and exciting platforms that I got to work on at NASA. And one of the most interesting aspects of it were these 3 engines here at the back of the shuttle. So these are the Space Shuttle main engines. They provide an enormous amount of thrust to the aircraft. It takes it from essentially stationary to orbit in about, I don't remember exact time, so I'm not going to say, but it gets up there very quickly, and it burns liquid hydrogen from this external fuel tank. So certainly a safety critical system, right? And one of the things that happened in one of these missions is that a valve inside of this SSME actually cracked. And this is a picture of the valve, and you can see this white shard here. That's actually broken metal. Now, what's interesting about this situation is that that broken metal actually flew down at probably at supersonic speeds down a metal pipe and fortunately, it didn't break it. But if it did break it, it almost certainly would have been a catastrophic event on the shuttle. Now, the question was, this happened, and I got a phone call, if I remember right, on Valentine's Day many years ago, and they said, can you take a look at the data from these systems and see whether or not the algorithm could have detected that problem? So again, another anomaly detection problem. So the idea here is that we've got a whole bunch of data coming off of those SSMEs. We want to see if there's some indicator of that particular problem in it. So here is the analysis that we did. On the x-axis, we've got time, and on the y-axis on this panel, we have an anomaly score. Now, this anomaly score is not generated through that kernel method that I described, or in fact through the method that I first described of just doing what we call envelope detection, where some parameter is out of whack, and then you just say it's out of whack. This is a different approach, which we called a virtual sensor, which essentially takes data from a number of sources on the shuttle, and it predicts a quantity. In this case, as I recall, we were predicting the pressurization in the gaseous hydrogen line. Okay? So you've got to imagine that you've got an engine. That engine is running, and you're getting a whole bunch of measurements off of that engine. And you're going to use those measurements in order to predict the value of pressure at a specific unit of time, the value of pressure in that line. And the idea was, let's say that we say that the value is going to be, I don't know, 50 pounds or however they measure it. And it actually turned out to be 70 pounds. Then you'd say, well, the pressure differential is 20. And so that's a certain number. And you can kind of imagine making a prediction and then getting the real value and taking the difference every time. Now you might say, well, why do that? Why not just look at the value itself? The reason is that it's very difficult to know, as the shuttle is going through its various stages of flight, what the correct value is. But if you think about it as a statistician would, he or she would say, conditioned on the state of flight, that pressure should be known. If you don't condition it on the state of flight, in a mathematical sense, then it's hard to say where it should be. But if I said, look, the shuttle is a mile off the ground, it's flying at Mach 3, it is, has this certain attitude, you could imagine saying that, well, that must mean that the pressurization in this line must be this much, right? And so we formalized that through a machine learning approach, and we said, we're going to make the prediction, and we're going to take the difference between the real life and what we predict, and we're going to plot it on the screen here. So that's what we did. So upon ascent, right when the engines launch, there's a lot of fluctuation in these readings, and so this is the difference between what we predict using our virtual sensor and what actually happens. There's a lot of variation. But on this flight, you can see that it really stays within the boundary very nicely, right? And so for STS-118, for that particular flight, this was completely nominal according to the analysis that we did. Now let's look at this flight. It's a little bit different. So first thing that you see here is that there are more transients. We didn't know if those transients were important or not. But right here, I'm sorry this this arrow isn't pointing to the right place, but right here at 93.6 seconds, you can see an abrupt change. So we were saying, the algorithm was saying, at 93.6 seconds, the value should have been a certain amount, but actually the pressurization was very different. And it increased, and it stayed higher than what we expected for the entire duration of the ascent. So over 450 seconds while those SSMEs were running, it was out of bounds. Now here's the really interesting part of the story. Other people at Kennedy Space Center and other experts found that exactly at 93.6 seconds is when that shard occurred. I'll go back to that slide. So that's when this metal piece broke, according to independent calculations. And the algorithm was able to detect that. But remember, it's good news, but only I need to moderate it a bit by saying that it was post hoc. After the flight, we got the data and we did this. It would have been much better if we were doing this during the flight and then we were able to see that type of an anomaly. But the point was that they said, based on these types of results, do you think that the current launch of the shuttle that was up in orbit at the time was safe or not. That was the next big question that we were asked to answer. And if you don't mind, I'm just going to give you a little bit of a personal story regarding this. So we were working on this whole thing, building the algorithms and everything, and working quite feverishly, my team and I, to make sure that we understood what was happening. And we had what's called a flight readiness review, in which many people, not just our team, but many, many people get on the phone and they say, are we ready for flight or not? And I really want to be clear. I was not, nor was my team, one of the key factors in it, but we were contributing. Really, really smart people at the agency spend literally day and night thinking about these flight readiness reviews, but we were very privileged to be part of that team for a little bit. So we went through the review, and one of the people at Johnson Space Center looked at this, and she said, what's happening there? And I said, well, these are transients, just like I told you, don't worry about them. And she made the comment, she said, I'm an astronaut, and if I saw something like that, they might be transients to you, but maybe there's information here. You have to go in and figure out if these transients are real, if they're important in predicting that or not. And so we did our very best to analyze that. We came to the conclusion that these transients were not in fact related to that, even though many other tests, I'm only showing you two, but many other experiments we ran showed transients of this nature, but we concluded that there wasn't a strong effect. Now, if you fast forward a couple of years, I was at a dinner of the AIAA, and I was sitting next to a person named Sandy Magnus, who was an astronaut at the time. And she was actually on the space station, and she apparently had heard about this type of analysis occurring. So we had an interesting conversation about it during that banquet. So I thought I would just tell you that it was an interesting way of tying all of these things together. This was a variation that we built on that algorithm where we allowed for adaptive thresholds, where these thresholds aren't fixed, but they vary conditioned upon the state of the aircraft at a given time. So you can see here that in this case, the transient window allows for these types of changes to occur much more than if we had just a straight red line. And so we explored all kinds of ways of building these types of algorithms and so forth. Again, a lot of anomaly detection and prediction and diagnostics problems being done here. I didn't go through the work that we did in earth science and astrophysics and everything, but a lot of it was guided by this idea that you should know the system that you're building and then build new and, in my opinion, cool ways of looking at it. So after leaving NASA, I totally loved NASA, but after leaving NASA, I thought that I'd take on a different challenge, and this was at Verizon. I was their chief data scientist. I left only a month ago, so a lot of this is quite new, still in my mind, or still very fresh in my mind. We built a very large platform for ingesting data, which we called the Orion Big Data and AI Platform, and built a very large team from scratch. So I think their target this year is 144 people. We built the entire hardware, software, and services architecture for it from scratch. We built all of the vertical products on top of it, and then we also sold it globally. And we did all of this in about 4 years. So it was a phenomenal experience. Totally loved it. And here's one of the things that we started to think about there. This idea of anomaly detection and prediction is very powerful, but it's much more powerful if you're able to put it into a situation where there's a great deal of automation, and finally, if there's a great deal of autonomy, right? In the ideal case, you would have a system which adapts to its changing environment, makes predictions, checks for anomalies, and does all of this in real time. So a lot of companies are doing this, a lot of researchers are doing this. Probably the most famous example today of this are self-driving cars and self-flying airplanes, self-fill-in-the-blank anything. There's going to be a lot of automation and a lot of autonomy that's being generated. But what's underlying a lot of it is this notion of adaptive control. So those of you who are familiar with the idea of adaptive control will look at this and probably blur your eyes a bit and say, hey, that's just adaptive flight control, which is true. That's the idea here, that you build systems that are monitoring data and that adapt to changing behavior. And we wanted to build this so that it could be done on the Orion platform as new data came on to that platform. So let me tell you a little bit about how we think about this. This dark blue box represents system behavior. So let's say your system is the population of the United States, about 100 million people, and their observations on the internet throughout the day and night. So that's the system that you're trying to model. So it's a very, very unusual system. So you've got a very large number of people, and they're each making different decisions as to what to look at on the internet. So some are looking at CNN, some are looking at Fox News, other people are checking Facebook, and other people are doing different things on their phones. And that type of data comes in onto the Orion platform now to the tune of about 70 billion records per day. And I'd say that they're on their way to do 100 billion very soon. So the question is, how do you model something like that? Well, simply put, you build algorithms to learn the behavior. And those algorithms need to be such that they can adapt to the changing environment. So as the news cycle changes, as the weather changes, as disasters occur, as different events occur across the country, it affects the way people use their phones, right? Obviously it does. How do you model something like that? Well, you build adaptive systems to do it, and I can tell you a little bit about those. Those need to be tied to and drive adaptive strategies. So if you're building an advertising system, you need to have that get informed by what's happening at this moment. And that moment is founded on two things. One, what you're doing in the cyber world, and two, what you're doing in the physical world. Right? So these two things have to fuse together as you build those adaptive strategies. And then that needs to go into some kind of a decision maker. So the decision maker, let's say for advertising, is which ad to show at what time and at which location. If it's an IoT, Internet of Things application, it's not serving ads, but it might be saying, should I take a measurement now or not? Should I take some other action or not? All of these things are, in my mind, completely the same thing. They're all related to the idea that you have to observe your system, build algorithms to understand the system behavior at different levels of granularity, take actions, and then drive those actions back into the system. So let me tell you a bit about Orion. It was such a fascinating thing to do. Great privilege to work at Verizon and built this kind of a system. So massive data processing, about 70 billion records ingested per day. The type of data is clickstream data and location data, as well as third-party data. Now, here's where a new angle comes into play. Because this is consumer data, you just can't use it however you want. Privacy and security comes into play here a great deal. And many of you are hopefully Verizon customers, and you might be wondering, so what's this guy doing with my data? Let me tell you what's happening on that platform. So it's actually an opt-in approach that Verizon took, which means that you have to give explicit permission to the company through easy-to-read language. I know it's easy to read because I helped participate in writing that language. Easy-to-read language that says, do you want your data to be used by us or not? And if you say, absolutely not, you click a button, and it actually doesn't show up on the platform at all. If you say, yes, great, then it shows up on the platform. And if you don't say anything, then what happens is we can only use that data for aggregate anonymous analysis. No PII information appears, at least while I was there, and so far as I know, no PII or personally identifiable information shows up on this platform. And yet we're able to do all kinds of very interesting things with the data and make very interesting and useful predictions. Let me give you an idea of the data set sizes that we were operating with. So this is supposed to be a matrix. And this matrix has 75 million rows. That's about the size of the population of data that we got on the platform. And about, that's a mistake, and about 32 million columns of data. It's a sparse matrix. So that means that most of it is empty, and there are a few observations of ones in it. And it poses a great challenge, extremely interesting area of work in large-scale machine learning. Right? Because you have to manipulate these kinds of matrices. And those of you who think about things from a linear algebra standpoint, you may have to do matrix inversions of things on the order of 32 million by 32 million. And we put in a constraint here that said we want it to be done in a few seconds. So that was the world that we lived in. And the exciting thing is we were actually able to do it. So we're able to make predictions. My former team is able to make predictions using data sets just like that with an arbitrary target vector in about a few seconds. And here's the real interesting part of it. Anyone can do it. So many of you here, I'm sure, are very technical. You could probably code this kind of thing in your sleep. But many of you may not be like that. I'll give you an example. My daughter, who's at the time 14, did not have any training to do this. But with a click of a few buttons, she was able to build algorithms like that and execute them on the Orion platform. And that's the way we did it. We wanted to democratize AI and machine learning so that anyone could do it, not just the chosen few. And so that was the crux of the work that was done. And we enabled then predictions, anomaly detection, regression, classification, clustering, and then also deep learning. And you'll see that it says down there, deep learning on the roadmap. So those of you who are in AI and machine learning and say, well, you know, what's going on with these people? Deep learning is where it's at. They should have done deep learning. I heard that a lot, and I understand the idea behind it. But let me tell you that there's a lot of value in building convex functions and using convex optimization to solve these types of problems because it's super fast. If you want to do processing on something of that scale and you want to do deep learning with it, number one, it can be done, but number two, it is computationally very expensive. However, if you use convex approaches, as we did, you can do this in a matter of seconds and get results that are very comparable. So this is work that we spent a lot of time thinking about. As a former person who worked quite a lot in neural networks and will continue to work in neural networks, we continue to pursue that. But I'd like to tell you a little bit more about the way we think about these kind of core computations on the Orion platform. So A is a matrix, that big blue thing that I said, 75 million rows, 32 million columns. And what we want to do is figure out different ways of representing A. And so this is one way of thinking about it. A is that matrix, and X and Y are two matrices that you don't know. Okay? And the question is, can you find an X and a Y such that if you multiply them together, it comes really close to A? So if you forget about the rest of the stuff here and just look at that, all this says is find me an X and a Y matrix such that if you multiply them together and take the difference that from A and square it up and add them up, that number is small. And if you do that, that's it. You could do it any way you want. You could write a genetic algorithm. You could generate random numbers. You could ask an astrologer. Anything you want to do, you could do it. And if you minimize that, that's all you're required to do. Right? Now, we put in a certain additional constraints. These are not new, by the way. A lot of people have worked on it for many years. But we put certain new constraints on it, or additional constraints, I should say, that says make X and Y small. Or if you get rid of the 2, it might say make X and Y such that the number of times they're non-zero is small. Those are kind of related, but they're not exactly the same thing. This is really interesting because if you do that, and if you can do it at scale, you've solved a huge number of problems all at once. You've solved regression problems at once. You've solved classification, anomaly detection, prediction. A lot of the things that people think about in machine learning get solved very quickly if you do this. So early on, when we were building the team, we built methods in conjunction with a colleague of mine at Stanford. We built methods that solve this problem at scale. And that's how we're able to do the kinds of calculations that I described, because we really looked at how to analyze this kind of equation, how to do the minimization when A is big, but A is sparse. So that's pretty much what I'd like to tell you about with regards to this. It's interesting. It's actually a non-convex problem, but we treated it as convex as we solved it. So that was Verizon. Now I'm going to tell you a little bit about Intuit, and then stop for questions. So I talked to you about like superconductors, and then about aeronautics and the space shuttle, and then about consumer behavior, modeling consumer behavior. Now this is something along the same lines, but it's a little bit more specific. If you look at what's happening in society today, there are a lot of people out there who are living paycheck to paycheck. the statistics show that apparently about 40% of the United States does not have $400 in case of an emergency. It's phenomenal to me that that's the case, right? If you look at small business statistics, I was looking at them last night, apparently the claim is that the vast majority of businesses fail in the first year. About 50% of ETF or NSF transactions, non-sufficient funds transactions, happen for values less than $50. There are all kinds of metrics. You can read about it on the Small Business Administration website and many other places. Lots of things that say that. And here's the other thing. About 99.9% of the firms in the United States are small businesses. Only 0.1% of them are big businesses. I think that's classified as larger than a certain number of people, right? So if you think about that kind of a scenario, there would be obvious, in my opinion at least, to use AI, machine learning, and so forth to help bridge that gap, to help make people make better financial decisions. And that's the mission of Intuit. My mission there is to bring AI and machine learning to bear so that people can make better financial decisions. And so you, your colleagues, the people around you that might be dealing with small business issues, dealing with personal finance issues, can have the benefit of all of the intelligence and knowledge that's embedded in the data sets that the company has in order to make those decisions. And here's the way we're thinking about it. The data comes in, very rich and accurate data sets capturing a lot of information about consumer behavior, about the payments and so forth. Development of a financial knowledge graph that represents the financial properties and the relationships between those properties. Machine learning to include all of the capabilities of diagnostics, prediction, mitigation steps, and then natural language processing. So here's a new aspect that we're going to be covering, which is to actually understand and model language that you and I speak and type on a daily basis. Taking all of these three things together, we want to build a human-level financial AI system so that now a person would be able to say, I'm, let's say, establishing a new flower shop down here on the corner of College Avenue and Laurel. For those of you who don't know, a long time ago there was a flower shop there, but what happened to it, we don't know. But it could be that that person might benefit from having these kinds of capabilities so that he or she would make better financial decisions. That's the whole idea here. Now, as we look at it, some of these things are quite hard to obtain for most places. The data sets, the financial knowledge graph. Some things are widely available and widely shared, like knowledge of machine learning and natural language processing. These kinds of things are widely available and and can be shared. But the company itself, Intuit itself, has access to a lot of this information directly. These hard-to-obtain pieces of information are available, as well as all of the AI and machine learning capabilities. And so as we put these things together, we hope to be able to address some of these societal concerns that are occurring all around us. So I'm going to now come to my conclusion and just talk about a couple of themes that I've looked at across the work that I've done in these various disciplines. First, importance of people. It is so cliche to say it, but it's so true that the ability to work with people and to develop partnerships is critical to getting any of these things done. Some say, don't worry about it, AI will take care of anything. I say, okay, but we still need to work with people and domain experts and get university collaborations and other types of things going. Develop applications that are consumer-facing and sometimes purely back-end applications. This kind of capability is essential to pulling something like this out. Having a strong foundation in machine learning, AI, statistics, and related areas at a working level is very important so that you have the ability to say, this is going to work and this is probably not going to work at an early stage. If you go down certain paths and spend a lot of time on them, sometimes it can be fruitful and sometimes it can be risky. So making quick decisions based on the kinds of observations that you're seeing and the type of data that you have is very important. Understanding the technology behind big data systems is very relevant to this type of work that I've done. How you take this type of data, how you organize it, how it's distributed across the system, how you access it, all of the underlying technology for both real-time and batch processing is super important. And then most importantly, how you collect the data. So where is it coming from? What's its provenance? What are your rights to access that data? Under what conditions can you use it? When can you not use it? When should you not use the data, even if you've got it? Those types of things are super important. So these things of legal, privacy, security, and governance, extremely important, in my opinion, for pulling off the type of work that my team and I have done over many years. And then a common thread is communication across all of these areas. So people who do this often don't think about that. And people who do this and this are often very different people. These people tend to be business people, or they tend to be domain experts. These people tend to be people who are technologists, scientists, and so forth. So bridging the gap between them is critical to success in this area. So let me tell you, we are hiring in all areas. So if there's any interest here from people in technology, from people in business or other areas, please let me know. We intend to build a team of probably 300 to 500 people just focused on AI and machine learning and Intuit. We're going to have people in Mountain View, California, San Diego, California, Israel, and then potentially in other areas as well. And so hiring in all of these areas, data science, we've discussed that, AI algorithms, so NLP, deep learning, all of those types of things, statistical machine learning, classification, regression, etc. NLP, software engineers who know about the algorithms, really important, program managers who know how to get things done, and then V&V, so verification, validation people who really know how to deploy things and test them at scale. So I'll stop there and see if you've got any questions. I very much appreciate your attention. It was a very great honor for me to be able to speak to you all today. Yeah.
Gravitational wave detection
Uh-huh.
presents an extreme challenge.
Yes.
The statistics they're using, is that good?
So I haven't, unfortunately, been involved with the gravitational wave studies that are being done by NASA, probably in the other universities that are around. But knowing many of the people that work in that field, I would say that absolutely they're using probably some of the most sophisticated techniques in that area. Are there any other questions? Yeah. Uh-huh.
If that's something that you guys have considered, if you have people talking about it, thinking about it.
Absolutely. So the ethics, so the question was, what about the ethics of using AI and machine learning in finance and probably in other areas as well? It's incredibly important, and it's something that I and my team take very seriously, and we do spend a lot of time thinking about how to use the data, what the right approach to using it is, and what the right use of it would be. So that's one area. And then the way of characterizing the algorithms that actually inform people on the decision-making process is incredibly important. That's why this is a foundational element to all of the work that happens above it. One last question? Yes, sir. Uh-huh.
So my question is, the data matrices that you often encounter, do they have special structure, like do they have low ranks?
Yeah, so the question is on this slide. On this slide, do we enforce low rank? And yes, we do. So X might have much lower rank. So again, if you remember, A has like 32 million columns in it. So X might have much smaller column value than A does. And so when you do that, what happens is that it constrains the amount of information. It forces the amount of information in X to be relatively low dimensional compared to A. And that gives you certain benefits. And if you think about deep learning, these autoencoder networks that people build, They do the same thing, except in their case, it's not a linear function. It's a nonlinear function. But it's the same idea that you get, quote, a low-dimensional embedding of A, and then you use that low-dimensional embedding to do either autoencoding or other types of tasks. All right, well, thank you again for your attention.
Ashok will be here for a few more minutes after the end of the segment. If you have any other questions. At this point, I want to present this class to Ashok. Present it to Ashok Srivastava in appreciation for your information science and technology center distinguished lecture.
Thank you so much. Thank you very much.